Swap. Here we go. So the first topic we are going to cover today is probability. So far, we've talked a bit about uncertainty in the environments where we want to deploy some sort of AI agents. But we haven't really formalized that uncertainty. We don't yet have a language to describe or a framework to analyze uncertainty. Today, I'm going to introduce the language and the framework for reasoning about uncertainty and stochasticity, about observations, about the environment, about the actions and such. For many of you, this is going to be a review. For all of you, everything I'm going to talk about today is going to seem intuitive, but since the remainder of the course is very, very dependent on these basic concepts, it's important that you all understand, or at least refresh your memory of these basics. And it's really important that you ask any questions or ask about anything you are doubtful, any concept that you are doubtful about during the lecture or in the course of this week before we start our next set of lectures in the coming week. So in this first lecture, we are going to talk about some new concepts like random variables, joint and marginal distributions, conditional distribution. We're going to introduce a few tools like the product rule, the chain rule, and one of my favorite rules in the entire universe, the Bayes rule. You'll see why. And we're going to talk about inference and independence. In the second lecture, I'm just going to give you a heads up. We are going to start talking about Bayes nets, and we are going to go deeper into the practical implications of what we are covering in the first lecture in AI. Okay, so as usual, we're going to begin with a toy example. This toy example is a game. We're going to call it Ghostbusters. A ghost is in the grid somewhere. We have a grid. We have a rectangular grid, and there is a ghost somewhere in the grid, but we don't know where it is. The objective is for us to find where the ghost is. Now, we, of course, as I mentioned, don't know the exact position of the ghost, but we do have a probe. We have a sensor that we can put on different grid cells and get a measurement of how close we are to where the ghost is. Now, these sensors are noisy, but they can still give us some indication of how close we are to the ghost. So if we are on the ghost, it can be red. And of course, as I mentioned, the sensors are noisy. So seeing a red cell is not necessarily a definite indication of where the ghost is. If it's orange, it means that we are probably 1 or 2 cells away. If it's yellow, it means that we are probably 3 or 4 cells away. If it's green, it means that we are most probably very far from where the ghost is. Let's look at a video demo of how this works. I have to check to see if I'm sharing audio. Let me see. Can you tell me if you can hear the audio from this video? Raise your hand if you could hear the audio. You couldn't? All right, I have to start a new share. Give me just a moment. Sachin, could you hear the audio? Let me see. Okay.
No, I don't.
All right. So let me redo the share. Okay, so it should be fine now.
Ghostbusters. So the idea here is that there is a grid. In this grid, somewhere there is a ghost who's hiding. We don't know where the ghost is, but we know there is exactly one. We can make measurements. If we happen to measure on top of the ghost, we don't know that we measured on top of the ghost. All we get is a color back. We get red, orange, yellow, or green back. These four colors, how they show up depends probabilistically on how close we are to the ghost. If we're on top of the ghost, usually we'll get red, but we could get green. It's not, we don't know ahead of time. It's a noisy sensor. If we're further away from the ghost, the probability of red goes down, probability of orange goes up, yet further away yellow will be the highest probability, and then yet further away green will be the highest probability. So let's see if we can find this ghost, and at some point, we get one shot at trying to bust it. So we'll just be kind of sensing, and then at some point we say we think we found the ghost and hit the bust action. If we hit it on the correct square where the ghost is, we win, get a lot of points, so high utility. If we bust at the wrong square, we lose. So maybe we start out here, green, not very close probably. Red, likely better, but again, we don't know that for sure, so we might want to measure around it. See what's going on here. A lot of green around it, so maybe that red was just a noisy measurement and the ghost isn't really all that close to over there. This looks more promising, where we often get a warmer colored measurement. So at this point we might say, well, yeah, this looks pretty good. It's noisy, but this is likely where the ghost is. We don't want to waste any more time. Let's take our chances and measure. But keep in mind that we just as well saw red over here. That just happened to be a very noisy measurement. Most likely, who knows? We don't know. There's a small chance the ghost is somewhere completely different or where we measured green. But let's try and see what happens. So let's take a bust action. Ghost remaining 0. We got him. All right. So this actually worked out better than it usually works out, with a beautiful red square somewhere else where the ghost actually is not. This is what we're after in this lecture, is dealing with these noisy measurements in a better way than just kind of intuitively looking at this and saying, well, maybe it's here, maybe it's there, let's give it a shot.
So these settings, this particular toy example, is representative of the general settings of dealing with uncertainty in AI. In these situations, in general, we typically have, or may I say, we need to have some observed variables or evidence which represent what the agent knows about the state of the world. For example, sensor readings in Ghostbusters, or imagine a medical diagnostics scenario where a doctor wants to diagnose a patient with a particular disease. In that case, the observed variables are symptoms, whether the patient is coughing or not, whether the patient has a fever or not. Now, there are unobserved variables, which means that the agent needs to reason about the situation, reason about from what's observed before. So, for example, in Ghostbusters, the unobserved variable was where the ghost, the position of the ghost. In medical diagnostics, the unobserved variable is the disease. What is the disease? Now, there is also another entity or another concept that is very important in these situations called the model. This is very similar to the terminology we've been using in MDPs or previously in search. A model is what the agent knows about how the known variables relate to the unknown variables. Now, the framework and the tool set of probabilistic reasoning gives us the means for managing our beliefs and knowledge given the evidence and the unknown or unobserved variables and the model. So let's dig a bit deeper into the basics of probabilistic reasoning. We are going to start by defining a few concepts. The first of which, the foundation of it, which is the notion of random variables. A random variable is some aspect of the world about which we may have uncertainty. A few examples of random variables, whether it's raining or not, and we can represent it with uppercase letter, capital letter R. Is it hot or cold, weather-wise? Is the current weather hot or cold? If we don't know whether it's hot or cold, if there's some degree of uncertainty involved, for example, you've been stuck in your homes for a few days and you may have not been able to go out because of the quarantine. So you may not know exactly whether the weather is hot or cold at this moment. The weather outside is hot or cold at this moment. You can represent that uncertainty about the weather with the random variable t. Or, for example, after the quarantine, you may want to reason about how long it will take you to get to work. There may be traffic, there may be no traffic, there may be snow or icy conditions on the road, your car may break down. So there is some degree of uncertainty in how long it will take for you to get to work or get to school. And we can represent that with random variable D. Or in our toy example, Ghostbusters, we can represent the random variable L can represent the uncertainty in the position of the ghost. Now, this is a notational rule that we denote random variables with capital letters. Now, there's a similarity between the variables in CSPs and random variables. They both have domains. So for the random variable R, whether or not it's raining, the domain of possible assignments or possible values, possible outcomes, as we'll say later on, is true or false. It's either raining or not. And often we write it as plus lowercase r and minus lowercase r. So the outcomes are typically represented as lowercase, with lowercase letters. Is it hot or cold? The domain is hot or cold. Or alternatively, you can assume that this is a binary variable. It's either hot or not, so it can be plus t or represented as plus t or minus t. What about the time that it will take us to get to work or school? The domain of possible answers or assignments to this variable is essentially the domain of positive real numbers. Why not negative? Because typically we can't travel back in time, right? And it can take us a very, very long time to get there. What happens if, God forbid, we die on our way to work? That's why we have the upper limit of the domain set to infinity. And for L, the location of the ghost, the domain is possible locations, which is essentially the coordinates of all grid cells in the environment of Ghostbusters. Any questions so far? Are we clear on the definition of random variables? Okay, So as we move forward, I'm sorry, I can't view the chat window. If you need to tell me anything, please do so via voice.
It's clear, Professor.
Okay, all right, thanks. Now, let's introduce another concept, and it's that of probability distributions. A probability distribution is essentially a mapping of each possible value in the domain to a probability of its occurrence. So for temperature, where we represented our uncertainty about temperature with the random variable t, the possible outcomes, the possible values are hot and cold, right? The temperature can either be hot or cold. Now, this table here is an example of a probability distribution for the random variable t. It's telling us what the probability of each of these values or each of these outcomes is. So for the outcome hot, for the temperature being hot, the probability is 0.5, and the same is for cold. What about weather? So the weather can be sunny, rainy, foggy, or, well, you can consider the fact that there can be meteors coming from the sky. And this table here represents a probability distribution for this random variable W, weather. The probability of the weather being sunny is represented as 0.6. The probability of the weather being rainy is given to us as 0.1. The probability of fog is given to us at 0.3. Now, this one down here is interesting. The probability of a meteor, or let's make it simpler, a meteor shower, something that doesn't really threaten us, is denoted here as 0. It's important to note that it's really, really odd. It's very uncommon to encounter a probability of 0 in distributions representing real-life random variables. There's an underlying theoretical reason for this statement that the probability of 0 is very unlikely. It has to do with the complex system notions of how everything in this world is related to everything else. I'm not going to go deep into it, but it's going to be very, very uncommon to have a probability of 0 in the probability distribution of a real world random variable. So it's just to reiterate, unobserved random variables have distributions. And a distribution can be represented as a table of probabilities of values. This is another way of representing a particular mapping in the probability distribution. A probability of a particular assignment of a particular outcome is a single number. So we can represent the probability of this assignment, the weather being rainy, with this notation. The probability of the value or the assignment to the random variable W being rain is equal to 0.1. Now, there's a very intuitive yet very essential rule that we have to observe. For each possible outcome, or for each value in the domain of a random variable X, the value of the probability of that outcome should be greater than or equal to 0. This is because negative probabilities, negative values for probabilities don't make much sense. And the other very important rule is the sum of all probabilities in a probability distribution must be 1. Why? Well, essentially because at any given point in time, one of these outcomes is going to be true, right? And the only possible outcomes are those that are in the domain of this random variable. I know these two are very intuitive. I know that you're already familiar with this, but it's really important to reiterate these because we are going to make use of these two rules to construct a few analytical tools later on. Now, I have a question for you. For unobserved random variables, the mapping of outcomes to assignments is given to us by distributions. What about deterministic variables? Is there an equivalent of distributions for deterministic variables? If so, what do we call it? Any thoughts, any ideas? Raise your hand if you have any guesses you'd like to share with the class. Okay. So, just a quick hint. Where have you heard the term one-to-one mapping? Try to remember your introductory algebra classes and math classes, Calc 1. A one-to-one mapping in the realm of deterministic problems is called a function, right? So you can think of distributions as the non-deterministic equivalent of functions. Does that make sense? Any questions about this so far? All right. So one more thing about the notation. You can also represent the distribution or individual probabilities in a probability distribution using this notation. We call this just in this class, we are calling this the shorthand notation. So instead of saying P W equals P temperature equals hot, we just say P hot. And we can shorten this P of W being rain to P of rain. And it's okay if all domain entries are unique. This is just a notational rule to keep in mind. Now let's introduce another new concept, joint distributions. A joint distribution over a set of random variables specifies a real number for each assignment or each outcome. What does that mean? So a joint distribution of P of x1 equals this assignment or this outcome, lowercase x1, x2 having this outcome, x2, x, and remember the capital letters represent random variables, lowercase letters represent outcomes equals xn, and we can also represent this with a shorthand notation. We can just get rid of these the uppercase variables and represent it as such. So what does this mean? What does this mean? How can we interpret this? So essentially, It's telling us the probability of the first outcome being x and the second, the outcome of the first variable being x1 and the outcome of the second variable being x2 and such. For example, imagine you have two random variables, temperature and weather. The temperature can be hot and the weather can be sunny. What's the probability of these two assignments occurring in a particular outcome? Temperature being hot and the weather being sunny, these two are happening at the same time with a probability of 0.4. This is the joint probability of these two outcomes happening at the same time. What about hot and rain? It's 0.1. So it's very unlikely that the weather is hot and the temperature is hot and the weather is rainy, typically. What about the temperature being cold and the weather being sunny? It's 0.2 and so on. This data structure is called a joint probability distribution over the random variables t and w. Now, similar to the case of distributions, joint distributions must follow these two rules. First, the joint probability of each set of assignments, each of these probabilities should be greater than or equal to 0. It means that we don't consider negative probabilities because in this framework they don't make much sense. And also, the sum of these probabilities should be equal to 1. Why? Because at any given moment, one of these combinations is going to be true, right? Now, I have a question for you. What would be the size of the joint distribution table of n variables with each having a domain size of D? Just to translate that with an, just to simplify the question with an example, this is the joint probability distribution table for two variables, one of which, actually in this table, each of which has a domain of size 2. So temperature can be hot or cold, weather can be sunny or rainy. Now, how can we generalize this to figure out the size of this table? Ramu?
Square of the domain size.
Okay, that's one answer. Any other thoughts? Anyone else? So it's D2, Shantanu?
So, as well as the square of nth variable 2, no?
Okay, that's another suggestion.
And their multiplication.
All right. Anyone else? So let's see. Let me bring up the annotator. So we want to figure out how many different sequences of x1, x2, I'm sorry for my handwriting, I'm writing these with a mouse, to xn we can have, right? So how many different choices do we have for x1? How many different things can x1 be? D, right? That's what the domain means. The first item in this sequence can have D different assignments. What about the second item? It's the same, right? It can also have D assignments. What about the nth option? It also has D possible different assignments. So how many different assignments in total can we have for this sequence or for this tuple? It's D multiplied by D multiplied by D all the way to the end. How many of these multiplications do we have? N times. That's a number of variables. So the size of a joint distribution of n variables, each with a domain of size D, is D to the power n. What's the takeaway from this calculation? The takeaway is, in real world scenarios, when you're dealing with real world environments, or in general, when we're dealing with a large number of variables with large domains, this table is going to become very large, and it may be intractable to store or do computation on the joint distribution table. Later on in this lecture, we are going to talk about ways of reducing this computation load. Okay? Let me close this. All right, any questions? Very well. Now let's introduce probabilistic models. Let me first clear everything here. All right. A probabilistic model is a joint distribution over a set of random variables. That's the definition of a probabilistic model. As simple as that. A probabilistic model is just a joint distribution. What does this have to do with our original definition of model? We said that a model in this domain tells the agent something about the relationship between known variables and unknown variables. This joint distribution, the joint distribution is also allowing us to reason about the relationship between random variables. It's telling us that if one, for example, if we observe the temperature to be hot, then we can reason about the probability of the weather being sunny or rainy. We'll see how that works later on when we get to inference. So in probabilistic models, we have, as we mentioned, a set of random variables with their domains. The assignments to those random variables are called outcomes. So for example, T equals hot. The temperature being hot is one possible outcome. The joint distributions say how likely certain joint assignments are, certain assignments occurring at the same time are. It's important to note that joint distributions or probabilistic models are normalized. It means that the sum of all probabilities in the joint probability distribution table should be 1. Now, this is something to keep in mind. We'll talk about this a lot more towards the end of this lecture. Only certain variables directly interact in the ideal case. We want to reduce the number of entries in this joint probability distribution table. We'll see, we'll talk about this a lot more as we move forward. Now, this is very similar and can be modeled as a CSP as well. Remember, in CSPs, we had variables with domains. Here we have random variables with domains. What would be the constraints in probabilistic models? constraints here are stating whether the assignments are possible or not. And ideally, again, we only have certain variables directly interacting with each other. So some of these assignments may actually be of lower probability. Some of these outcomes may be of lower probability. For example, the probability of the temperature being hot and the weather being rainy can be very low. So ideally, we can take this out of the equation and make the table smaller. Now let's define an event. An event is a set of outcomes, and we represent this set with the capital letter E. The set of outcomes is essentially the probability of those outcomes occurring at the same time. If you have a joint probability distribution, you can calculate the probability of any event, right? How? So what's the probability of the event that is hot and sunny? Well, we just look it up in the joint probability distribution table. The probability of temperature being hot and weather being sunny is given to us as 0.4. What about the probability that it's hot? So there are two rows in this table representing this outcome or this event. What would be the probability of this event? All we have to do is to sum of the probabilities of these two rows. It's 0.4 plus 0.1, which gives us 0.5. What about the probability that it's hot or sunny? So it will be the probability of the outcome being hot, it's 0.4 plus 1, plus, remember this is or, plus any other event or outcome where there is sun. So it will be the probability associated with this row, and it gives us 0.5 plus 0.2, 0.7. So typically, the events we care about are partial assignments. We don't often talk about the probability of both the weather being hot, the temperature being hot, and the weather being sunny. We just talk about partial assignments. This is a common type of formulation and problem that we'll have to deal with in AI and machine learning. Any questions about how we got these probabilities and the definition of events? Are we clear on this?
Yes.
Okay. Just to make sure that everybody is on board, if you're okay with everything we've talked about so far, can you raise your hands? All right. What about the rest of you? Bibek, are you okay with everything? Do you have any questions?
I'm good, Professor.
Okay. Ganesh, any questions? All right. So some of you did not raise your hands. I'm going to assume it's because you're not around. But if you do have any questions about what we've covered so far, ask me now. All right. Cool. Let's move on. You can lower your hands if you want. So let's do a quick example. Let's walk through a quick example. given this joint distribution, what is the probability of this event? X being plus X and Y being plus Y. Well, this is just a simple lookup, right? We just look at the table and find the corresponding row to this event. The probability of this event is thus 0.2, right? What about the probability of the event plus X? So we are assuming that X and Y are binary variables. They can either be true or false. Plus X means X is true. Minus X means X is not true. And the same goes for Y. What's the probability of plus X? Can anybody tell me? Ramu?
It's a 0.5.
That's correct, yes. So the probability of plus X is 0.2 plus 0.3. We just collapse these two rows together, which means that we sum these two together, which gives us 0.5. Wow, that's a big zero. What about the probability of the outcome being negative Y or positive X? So what's the probability of the outcome being negative Y? Where do we find negative Y? In these two rows. Satvika, would you like to give us the answer?
It's 0.5. Sorry, sir. It's 0.4.
0.4. How did you come up with this answer? Remember, this is or. Negative Y or positive X. So, Zishan?
So it's 0.2
Why?
because 0.4 divided by 2 is 0.2.
And where did you get 0.4 divided by 2?
Put the volume down. Yeah. So plus X minus Y 0.3 and minus X of minus Y 0.1. You add those two, you get 0.4 and you divide it by 2. So you get 0.2.
Okay. All right. Keep that thought. I want to see what Anudip has to say. Anudip? All right. Ramu?
It's 0.6, Professor.
Why?
Because it is R plus X plus minus Y. So we have two rows over there minus Y. That is 0.3 plus 0.1 and plus X are already counted. So there is another one which is remaining, which is 0.2. 0.4 plus 0.2, that is 0.6.
Okay. All right. So let's see if we can reason about this. We have a number of different answers. What is the probability of the outcome being plus X? The probability of the outcome being plus X is 0.2 plus 0.3, which is 0.5, right? We've already looked at this. What is the probability of the outcome being negative Y? It's
0.3
0.3 plus 0.1, right?
Yes, it's 0.4, Professor.
Should we add these two up to get the answer to the probability of this event? 0.5 plus 0.4? Ramu?
Yeah, we can, but there is a double we counted, like plus X and minus Y. Like we need to subtract the intersection of both.
Exactly, exactly. So since there's an intersection between the probability of the outcome being negative Y, and the intersection happens here, to get an honest and practical probability for negative Y or plus X, we first sum up the probabilities of plus x and negative y, and then subtract the probability of the overlap, which is -3. What does that give us? 0.2 plus 0.3 plus 0.1 plus 0.3 gives us 0.9. Now we subtract 0.3, the overlapping probability, which gives us 0.6. Any questions about this? All right, cool. Let's move on. Now, let's define another concept called marginal distributions. Marginal distributions are subtables in which some variables have been eliminated. What do I mean by elimination here? Are we going to get rid of certain variables? In some sense, but we retain their effect. Let's look at an example here. Given this joint distribution over random variables t and w, if we want to look at the probability of t only, all we have to do is to see what are the different outcomes for t. They are hot and cold. What's the probability of hot? The probability of hot is the sum of these two probabilities. 0.4 plus 0.1 gives us 0.5. And what's the probability of cold? It's the sum of these two probabilities. 0.2 plus 0.3 gives us 0.5. This table is called the marginal distribution of the random variable capital T. What about the marginal distribution of random variable W, the weather? What are the possible outcomes? The weather can either be sunny or rainy. What's the probability of the weather being sunny? It's 0.4 plus 0.2, which is 0.6. What's the probability of the weather being rainy? It's 0.3 plus 0.1, which gives us 0.4. Now, note that this is essentially a the formal representation of this process. The probability of a certain outcome, being x1, from a joint probability distribution is given by the sum of all probabilities, all outcomes, where x1 is assigned, and all possible x2s. We are iterating over possible assignments of the variable x2. This is essentially an intuitive but very important formulation. Another thing to note is these are all still valid distributions. Why? Because the sum of probabilities in each of these marginal distributions is still 1. Okay, let's do a quick example with marginal distributions. Given this joint probability table, let us find the marginal distribution for x. X is two possible outcomes, right? It can be plus x or minus x. What is the probability of the outcome being plus x? It's 0.2 plus 0.3, right? So it's 0.5. Well, imagine this is a 5. Now, what is the probability of the outcome being negative x? So negative x is given to us in these two rows of the joint distribution. It's 0.4 plus 0.5, which plus 0.1, which gives us 0.5. Now let's do the same for P of y. What are the possible outcomes? What's the domain of the random variable y? It's plus y and minus y, right? So what's the probability of plus y? It's 0.2 plus 0.4, right? Which gives us 0.6. Now, without directly calculating the probability of negative y, can you tell me what this value should be? But just looking at this value here, can you tell me what this value should be? Ramu?
1 minus 0.6, that is 0.4.
That's correct. So the sum of these probabilities should be 1. That's why this probability, without looking at the table of joint probability distributions, can be calculated as 1 minus 0.6, which is 0.4. Now, just to cross-check, if we add this 0.3 to this 0.1, we'll still get 0.4. Okay, any questions before we move on? Okay, another new concept, conditional probabilities. Conditional probabilities give us a simple relationship between joint and conditional probabilities. There exists a simple relationship between joint and conditional probabilities. So what do I mean by conditional probabilities? It means the probability of the outcome A given the outcome B, given that B has already happened. So let's think about an example. The probability of the weather being sunny, given that the temperature is cold. How do we calculate this value? How do we calculate the value of this probability? Using this very simple formula. The conditional probability of A given B is the joint probability of A and B, the probability of A and B happening at the same time, divided by the probability of B. One interpretation of this is essentially we are looking at what proportion of the B outcomes are also A outcomes. So let's look at a quick example. Given this joint distribution, what is the probability of weather being sunny given that the temperature is cold? So it's essentially we can calculate it by first finding the joint probability of A and B happening at the same time, the weather being sunny while the temperature is cold. So it corresponds to this value here, 0.2, divided by the probability of temperature being cold. What's the probability of the temperature being cold? It's the sum of these two probabilities, 0.5, which gives us 0.2 over 0.5, which is 0.4. Okay, now let's work through a couple of more examples. The probability, given this joint distribution, what is the probability of plus x given plus y? So it's a probability of the joint probability of plus x and plus y over the probability of plus y, which is, what's the probability of plus x plus y? It's given to us in this row here, 0.2. And what's the probability of the outcome plus y? We have to add this probability to this probability to get that, which gives us 0.6. And there we have it. Any questions? I'm going to skip over the other two. You can work through them yourselves afterwards. Any questions about the notion of conditional probabilities and how we calculate conditional probabilities? All right. Now, we can think of, I'm going to introduce a notion of conditional distributions. Conditional distributions are probability distributions over some variables given fixed values of others. What does that mean? So given this joint probability distribution over T and W, the conditional distribution of the variable W given the assignment of hot to variable T can be represented as such. So now that the assignment of T is already known, we can calculate these conditional probabilities for different values, different outcomes of W using the formula we just saw in the previous slide. And we can do the same for another assignment of T being cold. Now, these two together define the conditional probability distribution of W conditioned over T. Let's look at how we can construct these conditional distribution tables. Imagine that we have this joint distribution and we want to find the conditional distribution of W given T equals cold. How do we do this? Well, we first calculate the conditional probability of W being sunny given temperature being cold. How do we do this? Well, we use, it's essentially just the joint probability of the outcome S and C divided by the probability of the outcome being C, which is, what's this joint probability? Sunny and cold, 0.2, divided by what's the probability of the outcome being cold? 0.2 plus 0.3, which is 0.5. So this is 0.2 over 0.5. But let's see if we can decompose this further. What's the probability of T equals C? We can write this as the probability of W being S, T equals C. So it's representing this row here, this value here, plus the probability of W being R and T being equal to C, right? Okay, we already knew this. So what? Bear with me for a second. Now, let's do this for the other assignment of W, which is R. We can do the same thing. We can do the same decomposition and get the corresponding values, which give us the conditional probability distribution of W given the assignment of cold to the random variable temperature. Okay. Is there a way to make things easier in terms of computing conditional probability tables? Let's see. Essentially, what we're doing here, a process to calculate conditional probability tables starts with selection of joint probabilities matching the evidence. So the probability of the temperature being cold, remember we are calculating the conditional probability distribution W conditioned on the temperature being cold. So we essentially collapse this table into this table. How did we get to this table? Just to make sure that you're all following. The probability of temperature being cold, we have cold down here, and the two possible assignments of W, sun and rain. Now that we are talking about one particular assignment of this variable, we can just forget about these two rows in the joint distribution table. Now that we have this, now that we've completed this step, in the next step, all we have to do is to make sure that the sum of these two probabilities adds up to 1. How do we do that? We just normalize it. So how can we normalize these values into something that adds up to 1, but still makes sense in terms of the proportion of these probabilities? We just divide them by their sum. So it's going to be 0.2 divided by their sum, which is 0.5, and 0.3 divided by their sum, which is 0.5. What does this give us? This gives us 0.4. And this gives us 0.6. And thus, we have the conditional probability distribution table of W conditioned on temperature being cold. See how much simpler this was? See how much easier it was to get from here to here compared to what we did before, explicit calculation of these values? This is called the normalization trick, and you will get to use this normalization trick quite a lot in the coming lectures. So to sum it up, to make it more general, to give you a general formulation for the normalization trick, for calculating the the conditional probability distribution of this sort, first, we select the joint probabilities matching the evidence. So the evidence is temperature being cold. Then we normalize. How do we normalize? The normalization is essentially these probabilities divided by the sum of the probabilities. Any questions about this trick? Let's see how we can apply this. Let's do one example of normalization trick and work through it to see if we've fully understood this. We want to find the conditional distribution of X given the assignment of -y to variable y. And we have this joint distribution here. So in the first step, we select the joint probabilities matching the evidence. So essentially, we are going to select these two joint probabilities. We can get rid of these two, which results in essentially minus x plus y Oh, did I did it incorrectly? Yeah, I'm solving it for the assignment plus x. Sorry, let me clear everything. So the evidence is negative y. Where do we see negative y? We see it here and here. So the relevant joint probabilities, the matching joint probabilities will become plus x negative y, giving us 0.3. The joint probability of this outcome is 0.3. And we have negative x. I'm looking at this row now. Negative x. This is a comma. So it's this one. Negative y, giving us 0.1, right? Now, all we need to do to get the final answer is to normalize these probability values, just to make it look more like a table. How do we normalize? We divide each by the sum of these probabilities. What's the sum? It's 0.3 plus 0.1, which is 0.4. So it's going to be 0.3 over 0.4 for plus x. And what about for negative x? It's going to be 0.1, but this is 0.4 over 0.4. And this is the conditional probability distribution of P of the variable x conditioned on y being negative y. So it's really simple. It should be straightforward. Does anybody have any questions? Is the process clear? I'm going to ask you a question. I want to see who can give me the answer. Why do we normalize? What's the point of normalization? Why don't we just give these values? As the answer or as the conditional probability distribution of x given y is equal to negative y. Ramu?
Maybe for simplification, like we can calculate easily.
No, there is a more fundamental reason. Anyone else? Okay. So the reason is, as we mentioned before, in a probability distribution, the sum of all probabilities should be 1. So all of the probabilities in a probability distribution should add up to 1. In here, this isn't happening, right? 0.3 plus 0.1 is 0.4. Normalization is essentially converting these or modulating these values into values that add up to 1 and thus preserve that requirement or property of probability distributions that says all of the probabilities should add up to 1. Does that make sense? Any questions about that? All right. So, this is on the definition of normalization. We've already talked about the procedure. I'm not going to go over this again. We've discussed this enough. You can review it from the slide or the lecture notes after the class. I'm going to start talking about probabilistic inference. This is of a very, very high degree of interest and importance in AI. What does it mean? What does probability inference refer to? It's essentially computing a desired probability from other known probabilities, such as computing conditional probabilities from a joint distribution. Generally, in many of the problems that we encounter in AI, we compute conditional probabilities. So we have some evidence, for example, in the case of checking to see whether we get to work on time or not. If the evidence is there is no reported accidents on the road, we want to calculate the probability of getting to work on time, given this evidence, given this observation, given this assignment of value or outcome of a random variable. We want to see what this conditional probability is going to be. These essentially represent the agent's beliefs given the evidence. What does an agent reasoning about these random variables, believe would happen given a particular set of evidence or observations? It's also important to note that probabilities change with new evidence. So in this example of getting to work on time or not, we first get this piece of evidence, no reported accidents, and we assign this conditional probability of getting to work on time, 90%. Now we see that we gather more evidence. Not only there are no accidents, it's also very early in the morning, it's 5 a.m. So accordingly, the probability of getting on time conditioned on these two evidence or observations becomes 0.95. What happens if we add one more piece of evidence to what we had before? It's now raining. So now the weather conditions are a bit worse. This changes our conditional probability of getting to work on time to a lower value, maybe 0.8 or 80%. Observing new evidence causes beliefs to be updated. Now, how do we perform this inference? I'm going to talk about a technique called inference by enumeration. In the general case, an inference problem can be formulated with using evidence variables, what has been observed, things that the agent knows, query variables, what we are curious about, what we want to find out. Are we going to get to work on time or not? Or let's say evidence variables can represent the symptoms of a disease. And the query is whether or not it's a particular disease, whether or not it's flu or coronavirus. And there may be some hidden variables. Variables in the case of medical diagnosis, for example, the heart conditions, the level of fat in the liver and such are not directly observable by a doctor who's examining you. The doctor can only see whether you have a fever or not. They can ask whether you have a headache or not. These hidden variables may help in finding a relationship between the evidence variables and the query variable. But in general, since the doctor, or in the general case, the agent, does not have access to them, we have to find a way to perform our inference without relying on these hidden variables. So how do we go about inference by enumeration? We want to, first of all, this is the objective, just to formulate the objective. The objective is to find the conditional probability distribution of the query variable Q given these pieces of evidence. Of course, just as a side note, you don't necessarily have to have a single query variable. There can be multiple query variables, but for now we are going to study the single query variable case to understand the basics. So the first step in inference by enumeration is to select the entries consistent with the evidence, right? We have a joint probability distribution table. We are only going to select entries that correspond to our observations or pieces of evidence. This makes our probability distribution table, joint probability distribution table, smaller and more tractable for computation. In the second step, we sum out the hidden variables to get the joint probability distribution of query and evidence. What does that mean? I want to whet your appetite a little before I dive deeper into this. Think about this. We mentioned that these hidden variables are not accessible to the agent. For example, a general practitioner, a general doctor or a nurse that sees you at the emergency room during a quick visit does not necessarily have access to your liver enzyme levels or the CBC test results, cell blood count results. They may actually matter. They may actually matter a lot in the causal relationship between the symptoms, for example, fever, and whether or not you have a particular disease like coronavirus or flu, or maybe you're just suffering from liver failure or such. The doctor does not have access to these. So to make some sort of inference, we need to get rid of these variables in our calculations. How do we do that? So remember the joint probability distribution of Q, E1 to EK. These are evidence variables. This is the query variable that we want to reason about. We want to infer something about. We want to infer the conditional probability distribution of this variable given the pieces of evidence we've collected. Is essentially just summing the rows in the joint probability distribution table that correspond to Q and evidence over H. What does that mean? Can I explain it in a more I can. I'm going to explain this further in an example. I was going to draw the example here, then I noticed that I do have the example in the next slide. And then we normalize to, and the next step, the final step, is to normalize to find the conditional probability distribution. So far, step 3 and step 1 are exactly the same as what we did for finding conditional probability distributions from joint probability distributions. That's just a normalization technique. Now, let's talk about what's happening at step 2. Look at this example here. In this example, we have 3 variables. One is the season. It can be either summer or winter. Then we have a temperature variable, which can be either hot or cold. And then we have a weather variable, which can be sunny or rainy. Now, let's say we want to reason about or infer the conditional probability distribution of W, the weather variable, given that the current season is winter. So in this case, what's our evidence? Our evidence is S equals winter. What's our query variable? It's W. We want to infer something about W. We are curious about W. Now, in this scenario, what's a hidden variable? Can anybody tell me what the hidden variable is? Which one of these three variables can be considered to be the hidden variable? Anyone? Ramu?
Temperature?
Temperature, yes. So temperature and season may have a very, very close relationship with the weather. But in this particular example, we can consider temperature to be a hidden variable, right? It's something that we want to get rid of because the things that we are taking into account for this inference are only W and S. So how do we solve this? Remember our steps. Let me go back to the previous slides to do a quick review. First step, select the entries consistent with the evidence. Which entries in here are consistent with the evidence? Our evidence is the season is winter. So we are only going to consider these rows here. We can forget about all rows corresponding to the assignment of summer, the outcome of season being summer. That was the first step. What's the second step? Let's go back and see. Sum out over H, the hidden variables, to get the joint probability distribution of query and evidence. Okay, so let's do this. We want to sum out over the hidden variable. What's the hidden variable in this example? It's T, right? It's the temperature. What we want to find out is W. We want to find the joint probability distribution of W and season. Let me keep it in the same order. So S, W, and we want to find their joint probabilities. So for S, we already have an assignment, right? We already have observed that the season is winter. S has only one possible assignment then, and that's winter. What about the domain of weather? It can either be sunny or rainy. What's the joint probability of the season being winter and the weather being sunny? We have to look at these two rows. See, in these two rows, this condition is met. The season is winter and the weather is sunny. What's the joint probability distribution of winter and sunny? It's 0.10 plus 0.15, which is 0.25. What about weather being rainy? We have to look at these two values now. It's 0.05 plus 0.20, which gives us another 0.25. Now, what's the third step? If you remember, the third step is to normalize. Okay. What's the point of normalization? We want to bring these values or tune these values such that they sum up to 1. So for that, we divide each by the sum of these two probabilities. What's the sum of these two probabilities? It's 0.5. It's going to be 0.25 over 0.5 for for this table. Let me clear things up a little. Oops, not what I was looking for. Now we want to find the conditional probability distribution of W given winter, right? Essentially what we want to find are the values to the table W probability given S equals winter. And these values from what we have here are going to be for weather being sunny, the value is going to be 0.25 divided by 0.5, which is 50%. And for rainy, it's also going to be 50%. Again, 0.25 divided by the sum of these probabilities. Okay, are we okay with this example and the inference by enumeration technique? Any questions? Does everything make sense so far? All right, let us march on. There are a few obvious problems with this approach, with the inference by enumeration technique. Its computational complexity is very, very bad. So the worst case time complexity of inference by enumeration is in the order of D to N, where D is the size of the domain of each variable and N is the number of variables. Also, the space complexity is very, very, very risky when we want to store large joint distributions. It's the space complexity is also in the order of D to N, which means that when we are dealing with large problems, the computational cost of inference by enumeration is very high. In the next few slides and the next lecture, we are going to talk about approaches to mitigate the cost of complete or full-on inference by enumeration. First, I need to introduce a couple of tools that help us get there. The first tool is the product rule. Sometimes we have the conditional distributions, but we want to have the joint distribution. Sometimes we have P of X given Y, but what we are interested in is the joint distribution P of X and Y. We can solve this very simply using the product rule. The product rule is as simple as this. The joint probability of X and Y is the probability of Y multiplied by the probability of X conditioned by Y. How do we know this? Well, we know this from the definition of conditional probability. Remember this? The probability of X conditioned on Y is the joint probability of X and Y divided by the probability of Y. Now, all we've done here is we've brought this denominator over here. That's it. And this is going to prove very useful later on. It's going to be one of the more useful tools we get to exploit in solving inference problem and Bayesian learning problems, as you'll see. So let's do a quick example. We have the probability of W. For example, this can be weather. And we also have the conditional probability of D, or D condition on W. D can be wet or dry. But what we want to find out is a joint probability of D and W. So all we need to do is to apply this rule here, which gives us points. So for sun, for the weather being sunny and the condition being wet, can you try to fit those in here? We multiply P of sunny, 0.8, by P of wet conditioned on sunny, 0.1. So it becomes 0.08. And we can work through the rest accordingly. Now, let me ask you a question. How many of you believe that this is a distribution? Show of hands. Is this a distribution? Is this table giving us a distribution? How many of you believe that this is not a distribution? Show of hands. So I have 2 hands up, 3 hands up. Okay, Venkatesh, why do you think that this is not a distribution? Venkatesh? All right, yeah, go ahead. Well, I think you are experiencing some technical difficulties. I'm going to ask Zishan. Zishan, what are your thoughts on this?
Sir, that would not be a distribution because it doesn't sum up to 1. It is making it to 2.
Exactly, exactly. Note that the sum of probabilities in this table is not 1, it's 2. This table is actually 2 probability distributions, 2 conditional probability distributions. One is this one here, the other is this one here. We've stacked them together just to save some space, just for the case of, for the sake of simplicity and representation. But that was a good observation, Zishan. Thank you. Yes. What about this one here? Is this a correct distribution? Do these add up to 1? The answer is yes. You can check and see that these actually add up to 1. All right, another rule, another tool in our tool set for probabilistic inference and probabilistic reasoning. It's a chain rule. More generally, we can always write any joint distribution like this as an incremental product of conditional distributions. So this joint distribution, P of x1, x2, x3, can be written as P of x1 multiplied by P of x2 conditioned on x1 multiplied by P of x3 conditioned on x1 and x2. Why? Well, it's essentially the same formula. P of xy is equal to P of y multiplied by P of x given y, right? This is precisely what we're doing here. P of x1, x2, x3 is P of x1 multiplied by P of x2 conditioned on x1 multiplied by P of x3 conditioned on x1 and x2. In general, P of x1, x2 to xn is a multiplication over the index I of P of xi conditioned over x1 all the way to xi minus 1. This is very important, and as we'll see in the next lecture on Bayesian networks, it can help with many, many, many different real-world probabilistic reasoning problems. Okay, there's one more rule that I want to introduce before giving you a break. But before covering that rule, does anybody have any questions? Are we clear on why this always holds? In case you're curious, all you have to do is to write this as its equivalent from the product rule. Any P of xy is equal to P of y multiplied by P of x condition on y. And then you can prove that this equivalence always holds. All right, now the Bayes rule. This is a very, very famous and a super useful and fundamental rule in machine learning and AI. So there are two ways to factor a joint distribution over two variables. One way is what we've seen before. P of xy, this is a joint distribution, can be written as P of x condition on y multiplied by P of y, or equivalently can be written as P of y condition on x given P of x. Think about the difference of these two in practice. In one, we are assuming that we've observed the evidence y, and we want to reason about x. In the other, we say that we've observed evidence x, and we want to reason about y. Just to give you more context, I'm going to give you an example. In medical diagnosis, you can say the joint probability of you having a migraine and having a headache, or let's change this, having the flu and having a fever, the joint probability of having a flu and having a fever can be written, can be calculated by checking to see if you have a flu and then reasoning about the probability of that, having fever and reasoning whether that fever is causing the flu. Or you can do the reverse. You have the flu, you know that the patient has the flu, and you want to reason about the probability of them having fever. Okay, so what? If we divide one side by P of y, we get P of x given y is equal to P of y over x multiplied by P of x divided by P of y. All right. That's it. That's the Bayes rule. As simple as that. You can reason about x given y by looking at y given x. All right. Why is this so important? This is so simple, right? This is so simple and so intuitive. Why is this at all helpful? Well, let's just build one conditional from its reverse. All right, so we already know that. Now, in many machine learning problems, And in many practical artificial intelligence settings dealing with uncertainty, often one conditional is tricky, but the other one is simple or simpler. For example, imagine that you want to train an automatic speech recognition system, right? That's what ASR stands for. It's really simple. Well, it's relatively simple to get from language or written to solve for the conditional of audio. I'm going to represent audio as A, given text, right? Now, if we can find this probability distribution, is there a way that we can do the reverse? Get the audio as our evidence and convert it to text, or find the corresponding text? Yes, all you have to do is apply the Bayes rule. So to find the text corresponding to a piece of audio, you can first train or find this probability distribution, P of audio given text over P of audio multiplied by P of text, and you've solved the automatic speech recognition problem. Of course, there are a few nuances that I'm not pointing to at this in this slide. Later on, when we get to our machine learning lectures, we'll dive a lot deeper into how an actual automatic speech recognition model can be trained. But I hope that you see why this rule is so important, because it allows us to train models, train machine learning models that solve interesting problems for us based on previous observations of the inverse mapping. So for example, you want to train an image classifier. What you have is images to the corresponding label. For example, this, you have a data set comprised of images like this with labels saying that, hey, this is a human. Or you can have, and you can have images of cats saying that those images are corresponding to cat with labels noting that those are cats. And you can, based on that data set, you can calculate the probability of image given label, right? But what we are really interested in is the probability of labels given image. You want a model that takes an image and tells you what the label is. Using Bayes' rule, we can get from this to this. That's why it's so important. So, as I mentioned, this is one of the most important equations in AI. And we are really fortunate because one of the most important equations in AI is this simple. It's very simple. Let's look at an example of inference with Bayes' rule. Imagine we want to do diagnostic probability from causal probability. For example, symptom, we have the probability of, let's say, migraines giving headache. We have this conditional probability. We have the probability of migraines, and we have the probability of headaches. And we can use these to figure out whether headache corresponds to migraine or not. Does headache mean the patient has migraine or not? So let's say probability, let's say we have these probabilities, plus the probability plus m plus migraine is 0.0001. The probability of a person having migraine in the universe is 0.0001. The probability of having headaches with a patient who has migraines is given as 0.8. The probability of having headaches when the patient doesn't have a migraine is given as 0.01. Of course, this is an example. This is not realistic. How can we find the probability of the patient having migraine given that he has a headache? Well, we have the probability of having a headache given they have migraine. We have this value here. This is 0.8. We have the probability of migraine in general. What's the probability of occurrence of migraine? It's 0.0001. And we have to divide it by the probability of effect, right? What's the probability of having a headache? A patient has come to you and tells you that they have a headache, and you want to diagnose whether they have a migraine or not. To find the probability of them having a migraine, to diagnose them with migraine, the only remaining value you need to calculate is the general probability of headaches occurring. And that general probability can be found by summing these two up, right? Is that right? No. You have to find the probability of plus s from these conditionals. What's the probability of plus s? It's, remember this? It's the probability of headaches occurring if you have a migraine multiplied by the probability of migraine plus the probability of you having a headache but not having a migraine multiplied by the probability of not having a migraine. What's the probability of negative m? It's 1 minus 0.001. Now we can plug all of those values in and get a probability, which is essentially your confidence in your diagnosis that your patient has a migraine. All right. Well, actually, the example I've given in these slides is M being meningitis and the symptom being having a stiff neck, but the same reasoning and the same interpretation stands. And note that the posterior probability of meningitis is still very small. So this probability over here is very small, which makes sense. There are many patients who do have meningitis. It's supposed to be a rare disease. All right. Any questions about Bayes' rule or anything we've covered so far? Are we clear on the importance of Bayes' rule? If yes, please raise your hands. If you're happy with your understanding of the Bayes' rule and its importance and applications, raise your hand. So a few of you have not raised your hand yet. Venkatesh, do you have any questions? I think Venkatesh might be away. Shiva, any questions? All right, thanks, Venkatesh. Shiva? Any questions? Sachin? All right. Good. So let's take a 5-minute break and come back at 3:40 to start the second part of our lecture. I'm going to stop recording now. In the meantime, if you have any questions, feel free to ask. If you don't have any questions, you can lower your hands. All right, Sachin, do you have a question? Okay.
No, Professor, I'm good. I forgot to lower my